Hello, and welcome to a new chapter. This chapter will be mostly all, I think, about areas and perimeters. Reasonably important stuff. It's the kind of thing human beings have been doing about as long as they've been able to write. So, step one, something you probably already know. We have a square with side S. The area of that square equals S squared. Notice the similarity between square and square. That's not really an accident, I don't think. We square S to get the area of a square. Now there's a postulate. Actually, even in words, it's kind of short. It's even shorter if I do it in math, which says that if two polygons are congruent, then their areas are equal. So if I write, let's say, polygon 1 is congruent to polygon 2, then I can immediately say that the area of P1 equals the area of P2. You can't go the other way. You can't say if the area of P1 equals the area of P2, then the polygons are congruent. That's totally wrong. And I can give you a quick example of how wrong that could be. Suppose we have a height here. We'll call that h, just a little dotted line. And the base is b, and here's h. The area of this will be 1/2 hb. We already know the area of a triangle, but we're going to remind ourselves of it in just a minute. In fact, I guess I'm doing that right now, aren't I? 1/2 hb, or bh, is the area of the triangle. Well, suppose I make a square with area equal to bh over 2 and the square root of that. I've got a square with one side equal to the square root of bh over 2, whatever number that is. Well, when I get the area by squaring that, what am I going to get? I'm going to get this, bh over 2. That means I can make a triangle in a square with exactly the same areas. And in no universe would a triangle and a square ever be congruent. So, be very careful to keep in mind that this doesn't go two ways. It only goes one way. If the polygons are congruent, then you can say the areas are equal. But you can't go the other way. We have another postulate. It's pretty simple. It says that if we have any polygon, in this case we have a rectangle, I can break that up into non-overlapping sections, add up the area of each section, and that will equal the area of the entire rectangle. But they have to be non-overlapping. For instance, this one here, if I take it out, this red rectangle fits exactly into the empty spot here. But suppose I move it over so they overlap. Well, now it's not true anymore. I can't say that the area of the red rectangle plus the area of the blue rectangle will equal the entire area of this black rectangle. Also, if the areas in question don't completely cover the original, I can't say that either. For instance, it would be kind of hard to say it in this case because I got an empty spot here. And let's pretend this part over here doesn't exist. I just got, well, why pretend? There we go. There. Now it doesn't exist. Now I can't say that the area of the blue and the red, or actually it's not red, brick colored, they don't add up to the rectangle. This is only true if they completely cover the rectangle and they don't overlap. I'm going to do it that way. It doesn't quite cover, so it's not true. Now, if it covers and doesn't overlap, Now it's true. So keep in mind, to find any area you want, you can always break up that area into non-overlapping sections which completely cover the area. And we'll see why that matters in just a second. Now, by the way, if you're curious, that's called the area addition postulate. I think it's a postulate at this level, but the fact is, you could probably prove its truth. I don't think it really has to be a postulate. It may not be easy to prove, but I believe you could actually prove it. So let's take a look at this parallelogram. We've drawn in a height here, we'll call that h. Then we have a base, b. The area of this parallelogram is just b times h. That's kind of easy. But it seems kind of weird too. I mean, with all this stuff pushed over to the side like that, well, why does it turn out to just be the altitude times the base? Well, I've drawn a couple of blue lines in here, not by accident. We call this an altitude. This is perpendicular. It has to be. That's the whole deal with an altitude. We go from a vertex and drop it down to the base, perpendicular to the base. Now we have an altitude. I can go ahead and draw that in if I want. And there's another one here. Well, since this is the height and this is the same thing over here, these are both h. So these two are congruent. On the other hand, we have a parallelogram. So this side here, which is the hypotenuse of this right triangle, is congruent to this side, which is the hypotenuse of this right triangle. Well, now we have a leg and a hypotenuse, which are congruent. That's our HL theorem for right triangles, hypotenuse, leg. So these two triangles are congruent. And we just pointed out that congruent polygons have equal areas. That may not matter too much yet, but they each have 1/2 pH. That's pretty obvious. I mean, they're congruent. The salient parameters are the same. And this triangle is not BH, or even 1/2 BH, because this length here is not B. The whole thing is B. So let's call this L. Now let's call the section from here to here, from this line that represents the height, from that point where it intersects B all the way over to the right here, let's call that K. In other words, L plus K equals B. Now the area of this triangle is 1/2 BH. Area of this triangle is 1/2 BH. These don't overlap. That's not the whole area, but we can start adding up these sections, because this triangle, and there's a rectangle here in the middle. None of them overlap, and they completely cover the parallelogram, which means if we can add all these up, we've got the area of the parallelogram. We got this one and this one, so if we add these together, that gives us this area here and this area here. What about this? Well, this is just a rectangle. We already know the area for a rectangle is one side times the other, K times H. Well, let's do a little rearranging now. 1/2 BH plus 1/2 BH. That's just BH. And KH, well, there we go. And that's the whole area. Well, let's use our distributive property and write h Gee, I wish I wouldn't do things like that. I just by wrote 1/2 BH, because I'm so used to writing it that way for a triangle. But in this case, of course, that's not right. Our little leg for the triangle here is L. That was the whole reason for labeling it. And after labeling it, I just mindlessly stuck in a B. So don't be mindless. Let me fix that. Okay. Now if I actually put my brain in gear and write this out correctly, 1/2 LH, that's this length right here, plus 1/2 LH, plus K times H, that's the area of the rectangle. I put these together, 1/2 LH plus 1/2 LH is just LH. Now I use my distributive law. I pull out an H and I get H times L plus K. Well, L plus K we already decided was B. So I get H times B. That's the area of the whole thing, and that's the formula we had up here. And that's why it might look a little strange, but it actually does work out. And the reason is because we just break it up into 2 right triangles plus a rectangle. And those are all things we know how to find the area of. Well, that's bad English. Those are all things of which we know how to find the area. Now that we know how to find the area of a parallelogram, it's easy to, well, I'd like to say it's easy to see why. The triangle area is 1/2 BH. But this is kind of circular. A lot of books do it this way, so I should show it to you. But we just used the area of we used the area of a right triangle. That's true, so it's not quite as circular as I would think. We use the area of a right triangle to derive the formula for a parallelogram. Well, for this, we could actually use the formula for 2 right triangles to get at this, but there's no other way we can do this. Now that we've used our right triangles to arrive at a formula for parallelograms, we can now use the formula for parallelograms to arrive at a formula for any triangle. I have 2 congruent triangles here, but I know they're congruent because I made them that way. What happens if I just connect them up? I put this one on top of this one. Well, if they're congruent, and the one I just slid over on top of the original one, or next to the original one, is flipped. So we have that this bottom side here is congruent to this top side for this one. This side over here is congruent to this. Well, we have opposite sides are congruent. That means these sides have to be parallel, and we have a parallelogram. That's from a theorem in a previous chapter, which says that if opposite sides are congruent, then you've got a parallelogram, whether you want one or not. It just has to be that way. Well, we already know that a parallelogram is H times B. And these are 2 congruent polygons put together to form this parallelogram. Well, congruent polygons have equal areas, so each one of these is half of the whole. This triangle here is what we were starting out with, so it must be just 1/2 of BH, because the parallelogram would be BH. Real easy way to see what's going on with areas of triangles. And keep in mind, there's a big difference between a proof and something like what I just did. And in my opinion, one of the biggest differences is that a proof is a way to show to everybody for all time that something is true. It's not necessarily the best way to remember what's true and what isn't. There are lots of simple, easy ways to get at something that makes it believable and easy to remember. That's not necessarily a full-blown formal proof, but in terms of practical mathematics, I think it's more valuable. I'd rather have something that helps me remember the formula than something that's really hard to remember that only helps me prove that it's true, but when it comes time to do some practical mathematics, it doesn't really help me remember the actual formula I need to make computations. That's why you might see me frequently not pay too much attention to a formal proof, but give a demonstration that I think is easy to remember. Because for practical purposes, I think anything that's easy, what am I trying to say? It gives you an easy way to jog your memory into using the appropriate formula. That's probably better than an actual formal proof. Now here we have one of those find the error. Well, the area of a parallelogram is the base times the height. Well, 5 is not the height. Whoever did this is confusing the altitude or height with one side. If you want the area of this parallelogram, you multiply 4 by 6 and get 24, not 30. I hope this man's not a contractor. Well, here they were supposed to find the area of the parallelogram. That's the shaded area here. This out here, this is just to compute or see what the altitude is. Look at it that way. You extend, where am I at here? Here we go. You extend this off and then draw a line straight up, perpendicular, up to this vertex, in order to determine the altitude. So this 4 here, this is the altitude for this parallelogram. On the other hand, this base here, well, this is 3. So the correct answer is 3 times 4, or of course 12. The error here was to mistake this whole thing for the base. Although if you were actually working this problem, you probably wouldn't write this in, because there'd be no reason to. The distance from here to here, that's irrelevant. It has nothing to do with the area of this parallelogram. This horizontal line, which is an extension of the base, is only there to determine the height. It has nothing to do with much of anything. So don't try to include this section as part of your area calculation. It has nothing to do with the original parallelogram. Now here we're to find the area of this entire weird shaped thing. What have we got here? 1, 2, 3, 4, 5 sides. So this is a irregular pentagon. This line here, they drew it in for us to help us figure out how to compute the area. It's not really part of anything. The exterior is what forms the polygon. How do we figure out the area of this? Well, they drew this line in here, so it's kind of obvious for us to break this whole thing up into a rectangle and a right triangle. That's even easier. So we got the altitude right here. It's just the length of this leg. Goes from this vertex to this vertex. For a right triangle, that would be the altitude. And then we've got this base. And of course, for a right triangle, we could call this the altitude and this the base. After all, multiplication is commutative. So whether we multiply this times this, or this times this, it's the same thing. We have to divide by 2, of course. This side of the hypotenuse for this is 25. The only reason we need that is that we need 1/2 the altitude times the base. Well, we get the altitude as 25. That's real easy. But there's nothing anywhere in here that tells us what this is. However, we do have everything we need to compute this length. So maybe we got to start by doing that. And we get this squared plus this squared equals 25 squared, or we've done this before, 25 squared minus 15 squared would equal this length. Let's call it L. L squared. My calculator says that 25 squared minus 15 squared is 625 minus 225. That's 400. So L is the square root of 400. That would be 20. So now we have that this side is equal to 20. The area for the right triangle then must be 15 times 20 over 2. We can divide the 20 by 2, get 10. 10 times 15 is 150. What about this one? We got to add in the area of the rectangle now. That's 19 times 25. Let's see here. Let's put it over here. All right. Area of rectangle. This is the area for the triangle equals this. Oops. The area for the rectangle is 25 times 19. If we multiply this out, we get 475. Now, the entire area, as we know, is the area of this right triangle plus this rectangle. They cover the area and they don't overlap. And there's no blank spots. They don't overlap. Well, when I say they cover the area, that means there are no blank spots. And they don't overlap or intersect. I'm referring to set intersection. If you ran across that in Algebra 1, or if you've heard of it, the intersection of two sets would be the elements that they have in common. For instance, if I draw a set of stuff, this is a set of points, and that's a set of points. Well, this part here, that's the intersection of these two sets. That's all I meant. And what we're talking about here is that we've broken this up into areas which have no intersection. This overlapping part doesn't exist. That means we just add up the area of the triangle and the rectangle, which we've already computed them separately. We add them up and get 625, which just happens to be what the area of a square would be if it had this side. You can play around, see if you can figure out why that would be true. There's nothing particularly obvious about this shape that would say it would have to be exactly the same. This is a 3-4-5 right triangle. In other words, this isn't 3, 4, and 5, but if we multiply each dimension by 5, we get 5 times 3 is 15, 5 times 4 is 20, and 5 times 5 is 25. So we have our basic 3, 4, 5 right triangle here. But I still don't see, it's not immediately obvious to me why this would turn out to be exactly the same as the area of a square with this side. But like I said, fool around with it on your own if you're curious. Well, this would be simple to the point that your 6-year-old little brother could do it. We have the altitude and we have the base. So it's just b times h, or h times b, doesn't matter. But the reason your 6-year-old little brother might have trouble with this is the dimensions we're using. It doesn't say 2 point something feet, like 2.25 feet, and 2.2 something feet down here, or 4 point something feet. No. They give it to us in 2 different dimensions. They give it to us in feet and inches. So we have to convert to one or the other. Either change this to all inches, and this of course, or change it to feet with a decimal point. Either way, just keep in mind that you have to do the same thing both ways. You can't change this to inches and then change the other one to a decimal representation of feet. That will give you a completely messed up answer. You have to have dimensions that match up. So let's change them both to inches. 2 feet, that's 24 inches, right? 24 and 3 is 27. 4 feet, that's 48 inches. 4 times 12 plus 2, that's 50. Now I think we got something we can work with. The area of the parallelogram, as we know, is HB, but now we can write that H is 27 and B is 50. So if we were to multiply this out, we get 1350 square inches. That's B. What about this one here? They did give us the dimensions in feet, so maybe they expect the answer in square feet also. Well, how do we convert these inches to feet? You might say divide by 12. 12 inches in a foot. Not quite. Remember, this is 1,350 square inches. So we have to figure out how many square inches in a square foot, because we're going to want area in square feet. Area is not going to be in linear feet. This is length, this base is length. The product of the two is going to be square feet, square inches, square yards. So if you wanted this answer in feet, you would take this 1350 and divide it by 12 times 12. There are 144 square inches in 1 square foot. And that's probably pretty easy to see. I mean, suppose I draw, and suppose is the right word for it. That doesn't look much like a square, but pretend it is. If it's 12 inches on a side, it's 12 here and 12 here. So how many inches would this whole thing cover? 12 times 12, or 144. On the other hand, if you do it in feet, this is 1 foot by 1 foot. We have 1 square foot, or 12 by 12 in inches, which is 144 square inches. 1 square foot, 144 square inches. And that turns out to be 9.375. Assuming you have an instructor or a home schooler, he can tell you whether one of these is more acceptable than the other. Personally, I don't see what's wrong with converting it into inches and giving the answer in inches. If they specifically ask for square feet, well, fine, then obviously you convert it to square feet. But the funny thing is both of these answers are correct. Here's one we're going to use some of our trigonometry. After the chapter on trigonometry, we really haven't used it much. So you're probably dreading this one. I don't blame you. We just have to remember that what we've studied of trigonometry, it applies to right triangles. So the first thing we have to do is figure out where a right triangle is going to come into this. And I think that if we drop a line, in other words, draw our altitude here, we can produce a right triangle just like we did when we were demonstrating how to arrive at the formula for the area of a parallelogram. And it's always hard to remember which is which. Remember our cosines and sines and tangents, they're all the ratios of something over something. We just have to figure out and remember what the somethings are. For instance, I use the mnemonic. Some old hippie caught another hippie dripping on acid. So sum starts with S, so that's the sine, old hippie. That's opposite over hypotenuse. Well, here's our angle here. Here's the opposite, and here's the hypotenuse. So I think we can write that the sine of 20 degrees equals opposite over hypotenuse, L over 8. So if we write it out that way, do a little rearranging, we get that L is 8 times the sine of 20 degrees. If you look this up, and I don't know any other way to figure out the sine of 20 degrees, no one expects you to know it or compute it. You just look it up or punch it into your calculator. And the product of sine of 20 degrees and 8 is 2.736. So L, when this angle right here, DAB, equals 20 degrees, L would be 2.74. I'm not going to write that in because we're going to do it again for 50 degrees. They also ask about the area if this is 20 degrees. Well, now that we know what L is, we have the base. So our area when it's 20 degrees, I'm going to do it up here, what the heck. Matter of fact, what I need to do. There, just give myself a little more room here. The area, remember, is the base times the height. In this case, we're going to use 2.736, or, well, 2.74, times 15. And if we multiply this up, we get that 2.74 times 15 is 41.1. Yeah, it makes sense. If this were a 3, then this would be 45, right? So a little less than 3, a little less than 45. So our answer makes sense so far. After all, 20 degrees, I didn't draw this properly for a 20 degree angle at all. But this shows that the picture doesn't have to be accurate. As long as we pretend this is a 20 degree angle, we can still get all the numbers right. So 20 degree angle would be much smaller, and L would be real small here. Now let's do it again. But this time, it's 50 degrees. Well, I just leave all this here, since a lot of this doesn't, the only thing that changes is this part right here. So let's draw a line under this. Literally, and separate this off too. I don't want to get these equations confused with each other. Now, if this is 50 degrees, all we have to do is write the sine of 50 degrees equals, everything else stays the same. L is still the opposite. 8 is still the hypotenuse. So in this case, when L is, maybe I should have gone like L sub 20 and L sub 50. Can I do that? Yeah, why not? L sub 20 is this. L sub 50, that's L1. This angle is 20 degrees, and then here is L1. This angle is 50 degrees. And equals 8 times the sine of 50 degrees. Well, if I work this out, the sine of 50 degrees is about 0.766. Multiply that by 8, and we get 6.13, which is, this drawing looks more like this than this here. In other words, this looks more like 50 degrees than 20. So L for the second part, the drawing makes a little bit more sense. If L is 6.13, well then our new area, let's say a area when it's 50 degrees, and this is the area when it's 20 degrees. Well, that's still BH. But now H is 6.13. B hasn't changed. I think I wrote an 8 in here. In fact, I'm sure I did. That was totally wrong. Of course, it's the same as this. Our base hasn't changed. One more dopey mistake from this guy. That would be me. So 15 times 6.13, that gives us about 92. Oh, 15 times, that makes sense. 15 times 6 is 90. So 0.13 makes it 92. Okay, so we have a sensible answer here. We have a sensible answer here. The only thing that was maybe tough about this problem was you had to go back and remember the trigonometry that we haven't used for a while. But that's why I told you about the mnemonic. If you haven't used trigonometry for a while, I think you can always remember some old hippie caught another hippie tripping on acid. If you remember that, you can remember which ratio is which. And after that, it's really pretty easy. Once you got this thing, you just use your parallelogram area formula. It was remembering this part here that I think was probably the only thing that was a little bit tough about this problem. Now, the other tough thing is not making dumb mistakes like choosing 8 when you mean 15. But assuming you do things better than I do, and I'm sure you will, you won't have any trouble with problems like this. Well, that's about it for now.